Okay, so let's start with something familiar here. Number 1, Pythagorean theorem problem. 25-foot ladder leaning up against the wall. Bottom of the ladder is being pushed, now it's being pushed towards the wall at a rate of 5 feet per second. How fast is the top of the ladder moving? At this time, when the bottom ladder is 7 feet from the wall. Okay, so we're pushing the ladder towards the wall, so it's going to be going up as well. Okay, we know we're working with length of sides of a right triangle, so Pythagorean theorem. Derivative, don't forget time component. Okay, let's list out all of our variables. Okay, 25-foot ladder leading up against the wall. Where can we put that 25? Z, right? Yeah, length of the ladder. Bottom of the ladder is being pushed towards the wall at a rate of 5 feet per second. What is that referring to? Good, you're right. It's being pushed against the wall. That's causing the base of the triangle to be decreasing over time. So -5 for dx dt.
But only if it's like a triangle problem or like a shadow problem when it says pushing towards, that's negative. But if it was like a cylinder or something, it's positive.
I think with a cylinder, I think they'll probably have to give you descriptions. They'll have to tell you, oh, this value is increasing or decreasing. Okay. Probably wouldn't be as where they give you words to describe it. So yeah, I would say here they would just kind of give you these words. They wouldn't tell you whether it's increasing or decreasing. You have to kind of imagine it or kind of visualize it. But I think with the other geometric shapes, it will tell you. Okay, let's see. How fast is the top of the ladder moving up against the wall? dy dt. Good, that's the unknown. That's right, yeah. Ultimately, when we find our dy dt at the end, we should confirm that it's positive because y, our vertical component of our triangle, is increasing over time. When the bottom of the ladder is 7 feet from the wall. X is 7, yeah. Okay, we can find y by using the Pythagorean theorem. let's see. Still, what's dZdt here? The rate of change of the ladder. 0, right? Staying 25 the entire time. Okay, so we start entering information in. 7, 24, and 25, they all get inserted into our variable. dx dt is -5. And then we solve for dy dt. Good morning, morning. Sure, yeah. Okay, how does that look here? Okay, replacing everything except for dy dt, that's what we're solving for. And then add 70 to both sides. We are getting a positive dy dt, and that does correlate with what we expect out of our vertical length of our triangle increasing over time.
You want us to always put it in decimal form to the third?
Yes, to 3 decimal places. Yeah. Okay, number 2.
Can I ask a question?
Yeah.
Why is dz over dt equal to 0?
We're talking about the rate of change of the ladder. So this hypotenuse of a triangle is not going to change over time because of the property of this ladder. This ladder is going to stay 25 feet at the beginning all the way to the end of the problem.
Okay, so every time we see a question like that, will dz over dt always be 0?
If you can convince yourself that this is staying constant the entire time.
Okay.
So, but not every Pythagorean theorem is going to have a hypotenuse that is unchanging, just depending on the problem.
Okay.
Right. So, with Pythagorean theorem problems, you really need to kind of visualize the problem in motion and convince yourself, wait, okay, this is what I envisioned the problem looking like, and that will help guide your decision. Okay. Okay, a man is driving north at a rate of 17 meters per second. He sees a railroad track 20 meters ahead of him that is perpendicular to the road. Okay, so here's the perpendicular intersection. The train is going east on the track crossing the road. And the man determines with the radar gun that the engine is 35 meters away from him. And the distance between his car and the engine is increasing at a rate of 5 meters per second. What is the speed of the train? So here we have Pythagorean theorem, right triangle. I just like to have my horizontal being x, y, and z, but that's just my preference. Okay. Again, it's Pythagorean theorem. We can create our equation and our derivative. Okay, replace every variable. Well, sorry, we're going to list out all of our variables first. Okay, so a man is driving north at rate of 17 meters per second. What do you think this is referring to? Okay. Any adjustments needed here? Going towards it, right? Even though we're going north, I know a lot of times we associate up with positive, but in this case, that movement up is going to cause the distance between the car and the intersection to be decreasing over time. So we want that rate to be negative, right? We're basically saying that the distance between the car and the intersection is decreasing at a rate of 17 meters per second. Okay, he sees a railroad track 20 meters ahead of him. What would that be? Why? Engine is 35 meters away from him. What would that be? That'd be Z, yeah. Distance between the car and the train. Distance between his car and the engine is increasing at a rate of 5 meters per second. Yeah, DCPT. Positive or negative? Positive. Yeah, they take because they tell us increasing. Okay, we have two variables remaining. How can I find x? Yeah, Pythagorean theorem. That will give us that ability for us to solve for dx dt then. Okay, so 5 out of the 6 variables accounted for, we can solve for dx dt. And what do you expect out of dx dt? Positive or negative? Positive, right? That train is Distance between the train and the intersection is going to be increasing over time. We expect the dx dt to be positive. Okay, use your calculators. Okay, any questions? Okay. Just like what we expected, that dx dt to be positive. Everybody good? Okay, so part B, what is the rate at which the area of the triangle is changing? So now we're talking about the area of a triangle. So what's our formula for area of a triangle?
1/2.
We'll use the variables that I've already used to define the triangle. So I'll have to do 1/2 x times y. Okay, so I want to find the rate at which area is changing. I'm ultimately looking for which variable? dA over dt, right? Change in area. But to find dA dt, well, that left side is easy. A becomes dA dt, but on the right side, what do we have to involve? If I want to find the derivative. Product rule, good. X and y are different variables. They're being multiplied together. We have to rely on product rule. You guys know this one. Yeah, I'll give you, if it's other geometric shapes like, cones, cylinders, spheres, I'll give you that. Okay. Okay, so what's f prime? Good, right. So we still are tied to variable t here. Times y plus f. Okay, what's g prime? 1 dy dt. Okay, so that's the hard part. The hard part is trying to get to the derivative from here. Everything that we need is from part A. Right? We have dx dt, we have y, we have x, we have dy dt, everything that we need. Okay, let's try that. Now, at the end, what's our unit of measure going to be? Good, meters squared per second. So you find the units of measure for your numerator, you find your units of measure for the denominator, and just put them over each other. Okay, so go ahead and try that, see if you can get down to a numeric answer.
attention, the course maintenance person that needed the maintenance report back to the main office. Thank you.
Okay, any questions with part B? Yes.
So is it negative? You're getting triangle that's
Yeah, at this moment in time, the triangle is decreasing. I guess mainly because, yeah, y is getting closer towards, and x is moving away, but at this moment it is decreasing by this amount. Right. So normally we will never have area being negative, but we can have rate of change of area being negative. This means that the area is decreasing over time. Okay, let's go to next page. Okay, number 3, spherical balloon is inflated so that its volume is increasing at a rate of 40 cubic feet per minute. How fast is the surface area of the balloon increasing? Okay, we have our volume and our surface area equation given to us. Let's go ahead and find each of the derivatives, get all the calculus out of the way. All we need is power rule. There's no need for product rule. Remember, pi is just a coefficient. It just kind of hangs out in front as we take care of derivative of r. Okay, r cubed becomes 3r squared, dr dt. Okay, S becomes ds dt, 8 pi r dr dt. Okay, spherical balloon is being inflated, so its volume is increasing at a rate of 40 cubic feet per minute. Right. What variable is that tied to? dV over dt, positive or negative? Yeah, increasing. How fast is the surface area of the balloon increasing? Yeah, we're looking for ds dt. And the radius is 5 feet. Okay, clean this up a little bit here, dv dt. These cancel out. Okay, we're looking for ds dt. Where would you start?
All for DRDT. Or do for me for the
Okay, yeah, right. So sometimes the problem doesn't give us the radius. We had to find the radius. In this problem, previous problem, I think it gave you the surface area, and you had to kind of work backwards to find the radius. Here, they give you the radius, so we know that that is already ready for us to use. But yeah, we are missing that dRdt, and the connection with dRdt is we want to use dvdt to help us get there. Good. Okay, do a little bit of cleanup here. 4 times 25 is 100, 100 pi. Okay, divide both sides by 100 pi. Okay, make a note that pi is in the denominator. It needs to stay there. Doesn't matter how you reduce the fraction, but the pi is not going to be moved from the denominator. Okay, does everybody see that? That 40 over 100 does reduce, but the pi doesn't move. It still stays in the denominator. All right, so these are the missing pieces that we need, right? To find ds dt, which is our goal for this problem, we needed r, and we needed dr dt. Now that we have both pieces, we can solve for ds dt. Pi's cancel out, 5's cancel out. I'm left with 16. Okay, what's the unit of measure here? Yeah, surface area. So think about that word there, surface area, 2-dimensional unit, so square feet per minute. Oh, this 8 right here came from ds dt. When we find the derivative, we bring down the 2. So 2 times 4 pi is 8 pi r dr dt. Okay, any questions? Yes. That's right, yep. Surface area is always unit squared. Mhm. Are you A or B? Yeah. Okay. Yeah. Okay, one last one here. This is a cone problem. So we know we gotta work with similar triangles here. So paper cup 70 centimeters tall, diameter 60 centimeters. Oh, gotta use proportions here. So I can say radius of the small cone is to the radius of the large cone, as the height of the small cone is to the height of the large cone. I'm going to cross multiply, but I still don't know exactly which variable I want to solve for. I'll come back to that. Okay, let's gather some information here. A cup is being filled with water at a rate of 19 pi over 5 cubic centimeters per second. What is that referring to? We know it's a rate. We know it says to be a time component. Yeah, and why is that? Right, we see cubic centimeters. That's a hint. Three-dimensional unit is volume. Positive or negative? Being filled, right? Volume is increasing in the cup, positive rate. Okay, how fast is the water level rising? Or I'll call it H, right? dH dt. When the water level is 20 centimeters. H. Okay, put a star next to this because we don't want to use this value too soon. Do not use until the end of the problem. Okay, we are going to use it, but just not at the beginning. Okay. Now, these are some good hints, right? We are, even though we're not using this H, we know this is going to come in handy later. Everything that we're asking for and given is in terms of H, so that kind of helps guides our decision as to which variable we want to keep and which variable we want to find a replacement for. So what do you guys think?
Solve for R.
Mm-hmm.
So, because you're going to be DVDT formula.
Right, right. We want our equation in terms of H so that it will just naturally produce the variables that we want to use. Okay. If you solve for R, there's still a way. You can still do conversion through the proportion equation, but it's just faster if we can kind of plan ahead. Okay, so that means I want to solve for R, like you said. So solve for R so that I can replace R. Okay, so I have a suitable replacement for R now. R is replaced with 3H over 7. All right, any questions from here to here?
You don't use the 30 for the R. But it gave us in the problem because the diameters.
That's right, yeah. We use the 30 because of the radius, yeah. Okay, thank you so much. Okay, we do our cleanup here, distribute the exponent through so that we can get our equation ready for an easy power rule problem. Thanks so much. Okay, but we still want to do a little more cleanup, right? We want all the coefficients kind of pushed together. We want the variable kind of combined together here. So I'm just looking to clean this up quicker. So 3 and 9 can reduce to be 3. So I should get 3 over 49, but you can use your calculator if you like to do a little bit of cleanup that way. So the 3 and 9 reduces. I can push the 49 to pi, all that out to be 3 pi over 49. Make sure that you combine your h's. H squared times h becomes h cubed. So I just like to have my coefficients out in front without putting any numbers in a denominator space below my h. This should be a nice, clean power rule problem for us. Okay, any questions so far? Okay, so next up, find the derivative. V becomes dv dt. Coefficient stays. H cubed becomes 3h squared. And now it becomes easier, right? Everything that we need is ready for us to use. dv dt is here. H is 20, so now we can use H now that the derivative is set. And then we're solving for dh dt. Okay, what do you expect out of dh dt at the end? Positive or negative? Positive, right? Volume is increasing, so you expect your height to be increasing as well. dv dt gets replaced with 19 power over 5. H gets replaced with 20. we clean this up. Divide both sides by the fraction, which is the same thing as multiplying by the reciprocal. Pi's cancels out nicely. I guess in the calculator, I wasn't able to get this to clean up to a nice fraction, so I left it as a decimal there. Okay. Height is a one-dimensional unit, so centimeters for height. Time is seconds, so centimeters per second. Okay. Help session after school today and tomorrow morning as well. Mm-hmm.
Do we have a calculator on the test?
Yes, calculate on the test. Yes, both are recorded. Mm-hmm.
Thank you.
Thank you.
Well, Miss Virgo.